Welcome to this session on uniform flow. In this session, we'll be discussing on the flow through open channels. Open channel flow refers to the flow of fluid in the open channel to the atmosphere or partially filled conduit. For example, the river, flood, irrigation channels, sewers, carrying sewage, and roadside gutters are few examples of open channel flow. When you look at the picture, you can see the open channel flow which has a side slope and a bed slope which carries the liquid along the cross section of the channel. In piped flow, mostly it will be a circular cross section where there will be a pressurized flow of fluid inside the pipe. So for the open channel flow, the water surface will be open to atmosphere where it is a free surface exposed to the atmospheric pressure. Whereas in the piped flow, the full pipe will be completely flowing with the hydraulic pressure. When we look at the velocity distribution in the open channel flow and the piped flow, it can be visible that in the open channel flow along the upper surface or the at the top surface of the channel over here, the open channel flow will have an atmospheric pressure. Whereas in the piped flow, the maximum pressure will be at the center of the pipe and along the surfaces the pressure will be less. The free surface is an interface between the moving liquid and overlying fluid which will have a constant pressure. In the open channel flow, the moving liquid is most of the time water and overlying fluid is air at an atmospheric pressure. The driving force in the open channel flow is gravity because all the channels have a bottom slope. The shear stress on the free surface is zero. When we look at the velocity distribution across the cross-section of the open channel flow, the non-uniformity in the distribution of the velocity can be observed. This is mainly due to the free surface and resistance along the boundary for the fluid. The velocity can be measured using the pitot tube or current meter. The maximum velocity is usually found just below the surface. In a straight reach of the channel, maximum velocity usually occurs at 0.05 to 0.15 of the depth of flow. The geometrical properties of the cross-section of the channel affect the velocity distribution. The mean velocity is obtained by taking an average of the velocities measured at 0.2 meter depth and 0.8 meter depth from the surface. Here we can see the cross section of the open channel with a rectangular channel, a trapezoidal channel, a triangular channel and a cross sectional having a circular channel. Now looking at the different cross sections, we can see or we can observe that the velocity is maximum at a particular depth. Mostly it will be from 0.2 meter or 0.8 meter from the top surface. When we look at the fundamental equations governing the flow of liquid in the open channel flow, we have the continuity equation which is based on the law of conservation of mass. A1V1 equal to A2V2. And the second equation governing the flow is the Bernoulli's equation or the energy equation. And the momentum equation. These three equations govern the basic fundamental equation of the flow. The discharge through the open channel flow of various cross sections can be calculated by using the Chassis equation and the Manning's equation. The discharge through open channel by Chassis formula is given by V equal to C root over M into I or V equal to C root over R into S. V is the velocity of flow, C the Chassis constant and R the hydraulic radius which can be calculated as the wetted area divided by wetted perimeter and S is the slope of the channel bed. The discharge through the open channel by Manning's formula can be calculated by V equal to 1 by N, R per 2 by 3 and S per 1 by 2. V is the velocity of flow, C a Chassis constant, R wetted area by wetted perimeter, and S, the slope of the channel. The types of open channel flow are classified based on the time, space, Reynolds number and Froude number. In open channel flow, the Froude number is dominated as the Froude number is based on the gravity. So the different classification goes like this. The time-based classification gives the steady flow and unsteady flow. The space-based classification gives a uniform flow and varied flow. The Reynolds number classification gives the laminar flow, turbulent flow and transition flow. And Froude number classification gives the critical flow, supercritical flow and subcritical flow. The steady and unsteady flow classification is based on the time. Steady flow happens if the conditions like the depth, velocity, flow rate do not change with respect to time. And the flow in unsteady if the condition varies with time. For the classification of the uniform and non-uniform flow, the flow is described with respect to the length of the channel. So a flow in a channel is said to be uniform if the depth, slope, cross-section and velocity remains constant over a given length of the channel, and the uniform flow is possible only in prismatic channels. Uniform flow can be steady or unsteady flow, but uniform unsteady flow is rare in a real world situation. Flow in a channel is said to be non-uniform or varied if the depth, slope and cross-section and the velocity varies from one section to another section. For the non-uniform flow, we have two variations where we have a gradually varied flow, and if there is a very rapid variation, then we call it as a rapid varied flow. If the depth of flow in a channel changes gradually over a length of the channel, then we represent it as gradually varied flow. And if the depth of flow in a channel changes abruptly over a small length of channel, then we represent it to be the rapidly varied flow. The uniform flow and non-uniform flow will be represented based on the depth of flow variation. This picture describes the range or the classification of the uniform flow or the rapidly varied flow occurring along the length of the channel. When there is a sudden flow of water from a tank, then the flow undergoes a different variation through its flow. It will gradually have a rapidly varied flow, and for a stretch there will be a uniform flow, and when there is any obstruction, again there will be a sudden change in the depth of flow causing a rapidly varied flow. When there is a variation at or over a long period of length, then the flow will be in a gradually varied flow. The third classification is based on the Reynolds number. Both the laminar and turbulent flow can occur in an open channel depending upon the Reynolds number, which is represented by rho v r by mu. When the laminar flow, the Reynolds number is less than 500. For a transitional flow between the laminar flow and turbulent flow, we have the Reynolds number greater than 500 and less than 1000. And for turbulent flow, the Reynolds number will be greater than 1000. The Froude number is represented as Fv, which will be given as velocity divided by root over g into d. The Froude number forms the base for the open channel flow. The open channel flow is classified majorly based on the value of the Froude number. The Froude number is the inertia force by the gravitational force, or in other terms, the Froude number will be the water velocity divided by the wave velocity. So based on the Froude number, the channel flow can be classified into subcritical, critical and supercritical flow. Flow in open channel is said to be subcritical or tranquil flow or streaming flow when the Froude number is less than 1. In subcritical flow, the slow flow is there with a low energy state. In critical flow, the Froude number value is equal to 1. Here, the specific energy and specific force are minimum for the given discharge. Flow in critical state is unstable. For supercritical flow, where the Froude number is more than 1, the supercritical flow is at a shallow depth, the fast flow with high energy state. So based on the Froude number, the flow can be categorized as subcritical flow, a critical flow and supercritical flow. And based on this Froude number and the flow classification, the specific energy can also be calculated. For most of the economical section of the channel, the maximum discharge for the given cross-sectional area has to be attained. When the cross-section of the channel is going to be maintained as a constant, the velocity alone can be varied based on the continuity equation Q is equal to A1 V1 equal to A2 V2. When we have a long stretch of the open channel with the same cross-section, the A1 and A2 is going to be a constant one. So Q is equal to A1 V1 equal to A2 V2 for the continuity equation. So here the maximum discharge can be attained only when the velocity of the flow is maximum. So for the given value of slope, the velocity of flow will be maximum. The discharge can be calculated as area into velocity. Here the velocity is given by the Chassis equation C root over m into I or C root over R into S. If the hydraulic radius R is maximum when the wetted perimeter is minimum. If the wetted perimeter is minimum, then the discharge will be a maximum value. So based on this condition, the velocity can be calculated. V is equal to Chassis constant C root over A into I divided by root over P. So root over P is the wetted perimeter and A is the wetted area.